speed this is seldom the case. Also at supersonic speeds the divergent area is less than required to give complete internal expansion to ambient pressure as a trade-off with external body drag. Whitford gives the F-16 as an example. Other underexpanded examples were the XB-70 and SR-71. The nozzle size, together with the area of the turbine nozzles, determines the operating pressure of the compressor. Thrust, edit. Main article, jet engine thrust. Energy efficiency relating to aircraft jet engines, edit. This overview highlights where energy losses occur in complete jet aircraft power plants or engine installations. A jet engine at rest, as on a test stand, sucks in fuel and generates thrust. How well it does this is judged by how much fuel it uses and what force is required to restrain it. This is a measure of its efficiency. If something deteriorates inside the engine, known as performance deterioration, it will be less efficient and this will show when the fuel produces less thrust. If a change is made to an internal part which allows the air forward/combustion gases to flow more smoothly, the engine will be more efficient and use less fuel. A standard definition is used to assess how different things change engine efficiency and also to allow comparisons to be made between different engines. This definition is called specific fuel consumption, or how much fuel is needed to produce 1 unit of thrust. For example, it will be known for a particular engine design that if some bumps in a bypass duct are smoothed out, the air will flow more smoothly, giving a pressure loss reduction of X% and Y% less fuel will be needed to get the takeoff thrust, for example. This understanding comes under the engineering discipline jet engine performance. How efficiency is affected by forward speed and by supplying energy to aircraft systems is mentioned later. The efficiency of the engine is controlled primarily by the operating conditions inside the engine, which are the pressure produced by the compressor and the temperature of the combustion gases at the first set of rotating turbine blades. The pressure is the highest air pressure in the engine. The turbine rotor temperature is not the highest in the engine but is the highest at which energy transfer takes place. Higher temperatures occur in the combustor. The above pressure and temperature are shown on a thermodynamic cycle diagram. The efficiency is further modified by how smoothly the air and the combustion gases flow through the engine, how well the flow is aligned, known as incidence angle, with the moving and stationary passages in the compressors and turbines. Non-optimum angles, as well as non-optimum passage and blade shapes, can cause thickening and separation of boundary layers and formation of shock waves. It is important to slow the flow. Lower speed means less pressure losses or pressure drop when it travels through ducts connecting the different parts. How well the individual components contribute to turning fuel into thrust is quantified by measures like efficiencies for the compressors, turbines and combustor, and pressure losses for the ducts. These are shown as lines on a thermodynamic cycle diagram. The engine efficiency, or thermal efficiency, known as eta sub Th, is dependent on the thermodynamic cycle parameters, maximum pressure and temperature, and on component efficiencies. Eta sub COMPRESSOR, eta sub COMBUSTION, and eta sub TURBINE, and duct pressure losses. The engine needs compressed air for itself just to run successfully. This air comes from its own compressor and is called secondary air. It does not contribute to making thrust, so makes the engine less efficient. It is used to preserve the mechanical integrity of the engine, to stop parts overheating and to prevent oil escaping from bearings, for example. Only some of this air taken from the compressors returns to the turbine flow to contribute to thrust production. Any reduction in the amount needed improves the engine efficiency. Again, it will be known for a particular engine design that a reduced requirement for cooling flow of X% will reduce the specific fuel consumption by Y%. In other words, less fuel will be required to give takeoff thrust, for example. The engine is more efficient. All of the above considerations are basic to the engine running on its own and, at the same time, doing nothing useful, i.e. it is not moving an aircraft or supplying energy for the aircraft's electrical, hydraulic and air systems. In the aircraft the engine gives away some of its thrust-producing potential, or fuel, to power these systems. These requirements, which cause installation losses, reduce its efficiency. It is using some fuel that does not contribute to the engine's thrust. Finally, when the aircraft is flying, the propelling jet itself contains wasted kinetic energy after it has left the engine. This is quantified by the term propulsive, or Froude, efficiency, eta sub p, and may be reduced by redesigning the engine to give it bypass flow and a lower speed for the propelling jet, for example as a turboprop or turbofan engine. At the same time forward speed increases the eta sub th by increasing the overall pressure ratio. The overall efficiency of the engine at flight speed is defined as eta sub O equals eta sub P eta sub th. The eta sub O at flight speed depends on how well the intake compresses the air before it is handed over to the engine compressors. The intake compression ratio, which can be as high as 30:1 at Mach 3, adds to that of the engine compressor to give the overall pressure ratio and eta sub th for the thermodynamic cycle. How well it does this is defined by its pressure recovery or measure of the losses in the intake. Mach 3 manned flight has provided an interesting illustration of how these losses can increase dramatically in an instant. The North American XB-70 Valkyrie and Lockheed SR-71 Blackbird at Mach 3 each had pressure recoveries of about 0.8, due to relatively low losses during the compression process, i.e. through systems of multiple shocks. During an unstart the efficient shock system would be replaced by a very inefficient single shock beyond the inlet and an intake pressure recovery of about 0.3 and a correspondingly low pressure ratio. The propelling nozzle at speeds above about Mach 2 usually has extra internal thrust losses because the exit area is not big enough as a trade-off with external afterbody drag. Although a bypass engine improves propulsive efficiency, it incurs losses of its own inside the engine itself. Machinery has to be added to transfer energy from the gas generator to a bypass airflow. The low loss from the propelling nozzle of a turbojet is added to with extra losses due to inefficiencies in the added turbine and fan. These may be included in a transmission, or transfer, efficiency. Eta sub t. However, these losses are more than made up by the improvement in propulsive efficiency. There are also extra pressure losses in the bypass duct and an extra propelling nozzle. With the advent of turbofans with their loss-making machinery, what goes on inside the engine has been separated by Bennett, for example, between gas generator and transfer machinery, giving eta sub O equals eta sub P eta sub th eta sub t. The energy efficiency eta sub O of jet engines installed in vehicles has two main components. 1. Propulsive efficiency eta sub p. How much of the energy of the jet ends up in the vehicle body rather than being carried away as kinetic energy of the jet. 2. Cycle efficiency eta sub th. How efficiently the engine can accelerate the jet. Even though overall energy efficiency eta sub O is eta sub O equals eta sub p eta sub th. For all jet engines the propulsive efficiency is highest as the exhaust jet velocity gets closer to the vehicle speed, as this gives the smallest residual kinetic energy. For an air-breathing engine, an exhaust velocity equal to the vehicle velocity, or A. Eta sub P equal to 1, gives zero thrust with no net momentum change. The formula for air-breathing engines moving at speed V with an exhaust velocity V sub E and neglecting fuel flow is Eta sub P equals the fraction with numerator 2 and denominator 1 plus the fraction with numerator V sub E and denominator V. And for a rocket, Eta sub P equals the fraction with numerator 2 times open paren the fraction with numerator V and denominator V sub E close paren and denominator 1 plus open paren the fraction with numerator V and denominator V sub E close paren squared. In addition to propulsive efficiency, another factor is cycle efficiency. A jet engine is a form of heat engine. Heat engine efficiency is determined by the ratio of temperatures reached in the engine to that exhausted at the nozzle. This has improved constantly over time as new materials have been introduced to allow higher maximum cycle temperatures. For example, composite materials, combining metals with ceramics, have been developed for HP turbine blades, which run at the maximum cycle temperature. The efficiency is also limited by the overall pressure ratio that can be achieved. Cycle efficiency is highest in rocket engines, ~60+%, as they can achieve extremely high combustion temperatures. Cycle efficiency in turbojet and similar is nearer to 30%, due to much lower peak cycle temperatures. Typical combustion efficiency of an aircraft gas turbine over the operational range. The combustion efficiency of most aircraft gas turbine engines at sea level takeoff conditions is almost 100%. It decreases non-linearly to 98% at altitude cruise conditions. Air-fuel ratio ranges from 51 to 131. For any type of combustion chamber there is a rich and weak limit to the air-fuel ratio, beyond which the flame is extinguished. The range of air-fuel ratio between the rich and weak limits is reduced with an increase of air velocity. If the increasing air mass flow reduces the fuel ratio below certain value, flame extinction occurs. Consumption of fuel or propellant, edit. A closely related, but different, concept to energy efficiency is the rate of consumption of propellant mass. Propellant consumption in jet engines is measured by specific fuel consumption, specific impulse, or effective exhaust velocity. They all measure the same thing. Specific impulse and effective exhaust velocity are strictly proportional, whereas specific fuel consumption is inversely proportional to the others. For air-breathing engines such as turbojets, energy efficiency and propellant, fuel, efficiency are much the same thing, since the propellant is a fuel and the source of energy. In rocketry, the propellant is also the exhaust, and this means that a high-energy propellant gives better propellant efficiency but can in some cases actually give lower energy efficiency. It can be seen in the table, just below, that the subsonic turbofans such as General Electric's CF6 turbofan use a lot less fuel to generate thrust for a second than did the Concorde's Rolls-Royce /Snecma Olympus 593 turbojet. However, since energy is force times distance and the distance per second was greater for the Concorde, the actual power generated by the engine for the same amount of fuel was higher for the Concorde at Mach 2 than the CF6. Thus, the Concorde's engines were more efficient in terms of energy per distance traveled. Rocket engines in vacuum. Model type first. Run application TSFC ISP, by weight, ISP, by mass. #/LBF times HG/KN times SSM/S. Jet engines with reheat, static, sea level. Model type first. Run application TSFC ISP, by weight, ISP, by mass. pound /LBF times HG /KN times SSM /S. Dry jet engines, static, sea level. Model type first. Run application TSFC-ISP, by weight, ISP, by mass. Pound /LBF times HG /KN times SSM S. Jet engines, cruise. Model type first. Run application TSFC-ISP, by weight, ISP, by mass. Pound /LBF times HG /KN times SSM S. Thrust to weight ratio, edit. Main article, thrust to weight ratio. The thrust to weight ratio of jet engines with similar configurations varies with scale, but is mostly a function of engine construction technology. For a given engine, the lighter the engine, the better the thrust to weight is. The less fuel is used to compensate for drag due to the lift needed to carry the engine weight, or to accelerate the mass of the engine. As can be seen in the following table, rocket engines generally achieve much higher thrust-to-weight ratios than duct engines such as turbojet and turbofan engines. This is primarily because rockets almost universally use dense liquid or solid reaction mass, which gives a much smaller volume, and hence the pressurization system that supplies the nozzle is much smaller and lighter for the same performance. Duct engines have to deal with air which is 2 to 3 orders of magnitude less dense, and this gives pressures over much larger areas, which in turn results in more engineering materials being needed to hold the engine together and for the air compressor. Jet or rocket engine mass thrust to weight ratio. Kilogram, pound, kN, lbf. Road 0410 nuclear rocket engine 2000 4435.27 901.8. J58 jet engine, SR-71 Blackbird, 2722 6001 150 34,005.2. Rolls-Royce /Snecma Olympus 593. Turbojet with reheat, Concorde, 3175 7169.2 38,005.4. Pratt & Whitney F119 1800 3991 20,507.95. Road 0750 rocket engine, 3 propellant mode 4621 10,188 1413 318,031.2. Road 0146 rocket engine 260 570 98 22,038.4. Rocketdyne RS-25 rocket engine 3177 7004 2278 512,073.1. Road 180 rocket engine 5393 11,894 152 933,078.5. Road 170 rocket engine 9750 21,507 887 1,773,082.5. F1 Saturn V first stage, 8,391 18,499 7,740.5 1,740,194.1. NK-33 rocket engine 1222 2694 1638 368,136.7. Merlin 1D rocket engine full thrust version 467 1000 and 3825 185,180.1. Comparison of types, edit. Propeller engines handle larger air mass flows, and give them smaller acceleration, than jet engines. Since the increase in airspeed is small, at high flight speeds the thrust available to propeller-driven aeroplanes is small. However, at low speeds, these engines benefit from relatively high propulsive efficiency. On the other hand, turbojets accelerate a much smaller mass flow of intake air and burned fuel, but they then reject it at very high speed. When a DeLaval nozzle is used to accelerate a hot engine exhaust, the outlet velocity may be locally supersonic. Turbojets are particularly suitable for aircraft traveling at very high speeds. Turbofans have a mixed exhaust consisting of the bypass air and the hot combustion product gas from the core engine. The amount of air that bypasses the core engine compared to the amount flowing into the engine determines what is called a turbofan's bypass ratio, BPR. While a turbojet engine uses all of the engine's output to produce thrust in the form of a hot high-velocity exhaust gas jet, a turbofan's cool low-velocity bypass air yields between 30% and 70% of the total thrust produced by a turbofan system. The net thrust, Fn, generated by a turbofan can also be expanded as F sub n equals m dot above sub e v sub h of e minus m dot above sub o v sub o plus bpr of open parent m dot above sub c v sub f closed parent, where E equals the mass rate of hot combustion exhaust flow from the core engine. O equals the mass rate of total airflow entering the turbofan equals C plus F. C equals the mass rate of intake air that flows to the core engine. F equals the mass rate of intake air that bypasses the core engine. Vf equals the velocity of the airflow bypassed around the core engine. V equals the velocity of the hot exhaust gas from the core engine. V equals the velocity of the total air intake equals the true airspeed of the aircraft. BPR equals bypass ratio. Rocket engines have extremely high exhaust velocity and thus are best suited for high speeds, hypersonic, and great altitudes. At any given throttle, the thrust and efficiency of the rocket motor improves slightly with increasing altitude, because the back pressure falls, thus increasing net thrust at the nozzle exit plane, whereas with a turbojet, or turbofan, the falling density of the air entering the intake, and the hot gases leaving the nozzle, causes the net thrust to decrease with increasing altitude. Rocket engines are more efficient than even scramjets above roughly Mach 15. Altitude and speed, edit. With the exception of scramjets, jet engines, deprived of their inlet systems, can only accept air at around half the speed of sound. The inlet system's job for transonic and supersonic aircraft is to slow the air and perform some of the compression. The limit on maximum altitude for engines is set by flammability. At very high altitudes the air becomes too thin to burn, or after compression, too hot. For turbojet engines altitudes of about 40 km appear to be possible, whereas for ramjet engines 55 km may be achievable. Scramjets may theoretically manage 75 km. Rocket engines of course have no upper limit. At more modest altitudes, flying faster compresses the air at the front of the engine, and this greatly heats the air. The upper limit is usually thought to be about Mach 5.8, as above about Mach 5.5. The atmospheric nitrogen tends to react due to the high temperatures at the inlet, and this consumes significant energy. The exception to this is scramjets, which may be able to achieve about Mach 15 or more, as they avoid slowing the air, and rockets again have no particular speed limit. Noise, edit. The noise emitted by a jet engine has many sources. These include, in the case of gas turbine engines, the fan, compressor, combustor, turbine and propelling jet /S. The propelling jet produces jet noise which is caused by the violent mixing action of the high-speed jet with the surrounding air. In the subsonic case the noise is produced by eddies and in the supersonic case by Mach waves. The sound power radiated from a jet varies with the jet velocity raised to the 8th power for velocities up to 600 m/s, 2000 ft/s, and varies with the velocity cubed above 600 m/s, 2000 ft/s. Thus, the lower speed exhaust jets emitted from engines such as high bypass turbofans are the quietest, whereas the fastest jets, such as rockets, turbojets, and ramjets, are the loudest. For commercial jet aircraft the jet noise has reduced from the turbojet through bypass engines to turbofans as a result of a progressive reduction in propelling jet velocities. For example, the JT8D, a bypass engine, has a jet velocity of 400 m/s, 1450 ft/s, whereas the JT9D, a turbofan, has jet velocities of 300 m/s, 885 ft/s, cold, and 400 m/s, 1190 ft/s, hot. The advent of the turbofan replaced the very distinctive jet noise with another sound known as buzzsaw noise. The origin is the shock waves originating at the supersonic fan blade tip at takeoff thrust. Cooling, edit. Adequate heat transfer away from the working parts of the jet engine is critical to maintaining strength of engine materials and ensuring long life for the engine. After 2016, research is ongoing in the development of transpiration cooling techniques to jet engine components. Operation, edit. In a jet engine, each major rotating section usually has a separate gauge devoted to monitoring its speed of rotation. Depending on the make and model, a jet engine may have an N1 gauge that monitors the low-pressure compressor section and forward/or fan speed in turbofan engines. The gas generator section may be monitored by an N2 gauge, while triple-spool engines may have an N3 gauge as well. Each engine section rotates at many thousands RPM. Their gauges therefore are calibrated in % of a nominal speed rather than actual RPM, for ease of display and interpretation. See also, edit. 1 air turboramjet. 2 balancing machine. 3 components of jet engines. 4 intake momentum drag. 5 rocket engine nozzle. 6 rocket turbine engine. 7 spacecraft propulsion. 8 thrust reversal. 9 turbojet development at the ring. 10 variable cycle engine. 11 water injection engine. Notes, edit. 1.